Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about analog to digital conversion explained. Let's get started. Physical things like temperature, sound, and pressure are continuous analog signals, meaning they can take any value within a range. Digital systems give us efficiency, immunity to noise, and lower cost, which is why we use them so widely. The core challenge is taking analog inputs, processing them with digital circuits, and then converting back to analog when needed. We'll walk through the complete signal chain, starting from analog, converting to digital, and then back to analog again. You'll understand ADCs, DACs, the hierarchy of digital systems, and the role of logic gates. I'll show practical examples from everyday devices to make these concepts clear. Analog signals are continuous both in time and amplitude, meaning they don't have gaps or steps. For example, a microphone diaphragm, a thermistor, or a strain gauge each produce a voltage that varies smoothly. Digital systems, on the other hand, work only with discrete binary states, 0 and 1. To move from analog to digital, we need two key steps: sampling and quantization. Sampling means measuring the analog signal at specific, evenly spaced moments in time. Quantization then rounds each measured sample to one of a limited number of levels. How precise this is depends on bit depth. More bits give you finer granularity between levels. A complete loop from analog to digital and back to analog involves four main stages. We start with an analog input, go through an ADC, then digital processing, then a DAC, and finally get an analog output. An ADC takes a continuous analog voltage and converts it into a multi-bit binary number. For example, a soil moisture sensor outputs 0 to 3.3 volts. An 8-bit ADC divides that range into 256 steps. So a reading of 1.65 volts converts to the binary number 100000000, which is 128 in decimal. There are several common ADC architectures, including successive approximation, delta sigma, and flash converters. Each one makes different trade-offs between speed, resolution, and how much power it uses. Once the signal is digital, it goes into a computer, a microcontroller, a digital signal processor, or even a calculator. These systems manipulate the binary data using programmed logic and instructions. Common functions are filtering out noise, compressing data, detecting patterns, and controlling actuators like motors or lights. In the digital domain, we can make perfect copies, correct errors, and perform complex math with high accuracy. Analog circuits would suffer from drift, temperature changes, and signal degradation over time. A DAC does the opposite of an ADC. It converts binary data back into a continuous voltage or current. This transformation typically uses summing weighted currents or voltages, where each bit contributes a different weight. For example, a digital audio player sends MP3 samples to a DAC, which reconstructs the analog waveform you hear through your headphones. Without a DAC, the output would just be a stream of unintelligible bits. For instance, 011000001 might represent the letter A, but you can't hear it. So the DAC is what enables a human-readable analog output after all that digital processing. Digital systems are built in a hierarchical way, from simple pieces up to complex systems. At the top level, we have subsystems like memory, the arithmetic logic unit, and control logic. Each subsystem is made up of modules such as registers, adders, and decoders. And finally, those modules are built from basic logic gates, the simplest building blocks. Logic gates implement Boolean functions. The basic ones are AND, OR, NOT, NAND, NOR, XOR, and XNOR. Each gate has a truth table that defines its output for every possible combination of inputs. For example, an AND gate outputs a 1 only when all of its inputs are 1. Inside a logic gate, we use components like transistors, resistors, and diodes to make the logic work. A typical study progression starts with logic gates, then Boolean algebra, then combinational logic circuits. After that, you move to sequential circuits like flip-flops and counters, then programmable logic, and finally microprocessors. The core principle throughout is that binary states are manipulated by deterministic, rule-based operations. This table shows several everyday devices, listing their analog inputs, the digital processing they perform, and the final analog outputs you experience. Analog and digital domains work together as partners, not competitors. Each has its strengths. ADCs and DACs are the essential translators that bridge the gap between continuous analog signals and discrete digital numbers. And logic gates provide the fundamental atomic operations that make all digital intelligence possible. As sensors and edge computing advance, we see growing demand for efficient, low-power analog-to-digital and digital-to-analog conversion. Understanding this complete signal chain helps you design better systems, from smart home devices to medical implants.